Welcome back. In this video, we continue our study of Chapter 4 and move to Section 4.2 about Taylor's formulae. So there are three forms of Taylor's formula, but they all involve the same idea. Okay, they involve approximating a smooth function by polynomials with some remainder. Okay, so first, what do I mean by smooth function? Smooth in general depends on the context, but in general it means that so a function is smooth if it possesses enough derivatives in a given discussion. Okay, so for example, in differential geometry, usually a smooth function is a C infinity function. Okay, in complex analysis, a smooth path is a path of class C1. Okay. So this is so you should look at the context. What do you mean by smooth? Okay, so the idea is the same. But there are three forms of Taylor's formula. They differ by the form of the remainder and by the assumption on the function, okay, on the smoothness assumption of the function, if we want to be precise. Okay, so there are little nuances, if you like. Okay, so the first form is Taylor-Young, second form Taylor-Lagrange, and third form Taylor-Cauchy or Taylor with the integral remainder. Okay, so we usually prove this in the case of a function from an open interval of R into R. So here are the exact assumptions. So the Taylor-Young. So the assumptions are the following. So we have assumed that f is n minus times differentiable. Okay. And it's differentiable, its n minus 1 derivative is differentiable at the point A. Okay, so just assume differentiability at the point A. Then we can write f of x as a polynomial of order n, as you know, plus a remainder. Well, where the remainder is a small o of the distance between x and a to the power n. Okay, so we can write this in other forms if you like. So we can write it as a polynomial in x minus a or as a polynomial in h if you like. So you choose the form that you like, but all these are equivalent. Okay. So for h small enough, f of a plus h is f of a plus f prime of a times h plus 1 over 2 f double prime of a times h2 plus so on. The last term is 1 over n factorial times the nth derivative at a, which is just assumed to exist, times hn plus a small o of hn. Okay, so the remainder is a small o of hn in this case. This is Taylor-Young. Okay, we proved that in Math 1106. Okay, using basically the L'Hopital rule. Okay. Now, second form, Taylor-Lagrange. We put the assumptions on f are a little bit stronger. So we assume that f is n plus 1 times differentiable. Okay, so not only okay, so we put a slightly bigger, stronger assumption. So then in this case, we can write f as a polynomial in x minus a plus a remainder. And we have the remainder is the n plus 1 derivative at some point c divided by n plus 1 factorial times x minus 1 to the power n plus 1. Okay, now this is not very helpful if you cannot estimate c, because you just know that c exists. Okay, so it's not helpful if you cannot, but if we know now, I'll deduce a consequence. But this is actually an exact equality. Okay. So we can write f as a polynomial plus a certain remainder. And we would like that to show that the remainder tends to 0. Okay. So if we know that the n plus 1 derivative of f is bounded by some constant n, then the absolute value of the remainder, actually I put the so this is Rn of x. So this is Rn of x. So the remainder is bounded by a constant, this constant, divided by n plus 1 factorial, which is a constant actually, times h to the power n plus 1. Okay? And now this is a big O of n plus 1 for h small. Okay? And in this case, I can write f as an n-order polynomial in h plus a remainder which is of order n plus 1. Okay. So, third form, Taylor-Cauchy or Taylor with integral remainder, it's an exact expression. So, we assume that f is of class Cn plus 1. So the assumptions are even stronger than the assumptions of Taylor-Lagrange, but the result is better actually. If you noticed, the assumptions in Taylor-Lagrange were stronger than the assumptions in Taylor-Young, but the consequence was stronger. Okay, so. And Taylor-Cauchy, we have the same thing. We put stronger assumptions on f, and we get a remainder which can be written as an integral. So it's exact here. Okay. So this can be useful, but in general, Taylor-Young and Taylor-Lagrange are more used in practice as an asymptotic approximation of f. Because if you cannot estimate this remainder, it's usually useless. Okay. So we can rewrite it in two forms actually. So fa plus h as a polynomial. Here I just replace x by a plus h. And if I do the change of variables t equal a plus sh, okay, then you'll get this term here, hn plus 1. So you can write this as hn to the power h to the power n plus 1 divided by n factorial times this integral 1 minus s to the power n times the n plus 1 derivative of f at this point. Okay, and you can now put instead of as t if you like. So 1 minus t to the n fn plus 1 a plus th dt t between 0 and 1. Okay. So these are the three forms of Taylor's formula that we prove in first year. Now, as you expect, our target is to extend these three formulas to the case of a map between normal spaces. Okay? So, but for this, we have to give a new meaning to the notion of Taylor's polynomial. So, we know if f is twice differentiable at the point A, then its second order derivative at A can be thought of either a bilinear symmetric map, and use this notation instead of f double prime of A hh, just write h squared just to simplify, or also as a linear map from E into the space of linear maps from E, linear bounded maps from E into F. Okay, so we can consider f double prime of A at H alone as a linear map itself, so it needs another argument. Okay, we discussed this point of view earlier. And so more generally, we use this notation. So the nth order derivative of f at A, if it exists, is actually a symmetric multilinear map with n variables. Okay, so when all the variables are replaced by the same variable h, we get h n times. So instead of writing this, we write h to the n. Okay, so h to the n is a vector or an element in e to the power n, where all the components are the same. Because here all the variables belong to the same space, which is E. Okay. And in this case, Taylor's polynomial of order n will conserve its one-dimensional form that we discussed. But here now, instead, as we know, so f of A is a vector, is an element in capital F. F prime of A is a linear bounded map from E into F, so its value at H is an element in F. F double prime of A is a bilinear symmetric map from E times E into F, so it needs two arguments. And when I put instead of the two arguments HH, I get this. So this is an element in F, and so on. Okay, so the generalization will work, but we have to think of the derivatives now as multilinear maps instead of just numbers. Okay. Okay, and more generally, if we have a multilinear symmetric map with n variables, we write L of h to the n, or LHn without parentheses. This is just a notation, a shortcut, if you like, of this notation, the value of L at h n times. Okay, so this is a very useful notation. And now, what if we replace the first n-1 variables by h and the last variable by k? Then actually we get a function of k. And this function is denoted by LHn-1. Okay? So LH-1 is now a linear map from E to F. It takes an argument k and it produces this element of F. Okay, just replace the last one by k. But of course we can put the k anywhere we like because it's symmetric. Okay. So let us first establish an expected result that generalizes the familiar fact that the derivative of x to the n is nx to the power n minus 1. Okay, so here it is. If we have a symmetric multilinear bounded map, capital L, and we set g of h to be the image of L of the vector hn, then g is differentiable and its derivative at the point h in the direction k is n times the linear map evaluated at h minus 1 in the direction k. So this is just this action, but multiplied by. Or if you like, you can write g prime of h is n times the linear map hn minus 1. Okay, so this is really an extension of this formula. Okay, so here instead of x to the n, we take a multilinear map of h. So we can of course replace h by x. Doesn't change anything. So we can write g prime of x is n lx n minus 1. Okay, so this is an extension of this familiar fundamental rule of differentiation to the general context of normal spaces. Okay, so and I would use this. Let us prove it first. It's not difficult actually. We follow the same methodology that you use in the proof of this rule. How do you prove that? You can use induction if you like, of course. It's not, but it's the same idea. We can write, we take an increment k and we evaluate g of h plus k minus g of h. And we get this by definition. And now I use the linearity in each variable. So if I use the linearity in the first variable, I get L of h, and I don't change the remaining, plus L of k, etc. minus. So, and I repeat this reasoning n times. Okay. Or if you like, you can use induction. For example, if n equal 1, you just get L of h plus k minus L of h is just L of k. Right? If you have a bilinear map, and so on. So I can prove this. So the first, it's the sum of n terms. The first one, we have k in the first place and the remaining variables each. Second term, k is in the second place, and so on. And the last term, k is in the last. But now symmetry tells me that all these terms are the same. Okay, so I can write them as n L of hn minus 1k. Okay, so when I subtract, I get 0. And 0, of course, is a small o of k, right? So this exactly proves that g is differentiable at h and its derivative is given by n L evaluated at hn minus 1. Okay, so this is okay. Now I will use this to prove Taylor's Young theorem. Okay, the assumptions are f is n minus 1 times the Frechet differentiable, and its derivative, its n minus 1 Frechet derivative is differentiable at a. So, right, so we can just say this by saying that f is n times the Frechet differentiable at a. Okay. So here's the result. So f can be written as an n-order polynomial in h plus a remainder which is small o of norm of h to the power n. Now, I cannot write h to the n because h to the n was used to denote a vector. Okay, so it's better to be precise. And okay, we'll use induction. If n equal 1, this is just f of a plus f prime of h, and the remainder is a small o of norm of h, which is just small o of h, according to our convention. So Taylor-Young's becomes this equation, which expresses the Frechet differentiability of f at a. Okay, so the theorem is true for n equal 1. And now suppose that the theorem is true for a certain integer n, and for any map satisfying the assumption. So for any map which is n times Frechet differentiable at the point a. Okay, and now we take another map f, which is n times differentiable at a, which is n plus 1, because I want to prove the theorem for n plus 1. So I have to assume that fn plus 1 at a exists. Okay. Now, I want to prove that f of a plus h equal to this polynomial plus a remainder which is small o of h to the power n plus 1 in norm. So I introduced the new function which gives me the difference between f and its n plus 1 polynomial of order n plus 1. Okay, and I want to prove that phi of h is a small o of the norm of h to the power n plus 1. If I prove that, then the theorem will be proved for n plus 1. Okay, so I can differentiate phi in terms of h, okay, by using the rules. So the derivative of a plus h with respect to h, of course, is just f prime of a plus h. Okay, because I feel like this is just a particular case of the chain rule. This is a constant. Now the derivative of this, because this is linear and bounded in h, so the derivative is just f prime of a. And now we know how to differentiate this, because we can use the lemma now. The derivative of this term with respect to h is 1 over 2 factorial, it's constant, times twice 2 f double prime of a evaluated at h, okay, which is now a linear bounded map. And I do the same for all the other terms. Okay, so I apply the lemma to all these terms here. So I get f prime of a plus h minus f prime of a, which comes from this term, because this is 0. And the derivative of this term is just f double prime of a at h, which is now actually not an element in capital F. It's a linear map from E to capital F. Okay, so it needs another argument to become an element in the target space. And I get this. So the nth term will become 1 over n minus 1 factorial times the derivative of order n at a evaluated at hn minus 1. So this is once again a linear map. So phi prime of h is a linear map from E to F. Okay, and same thing for the last one. Okay, so if we apply the induction assumptions to f prime, so this is just so-called f prime equal g. So I have something of the form g of a plus h minus g of a minus g prime of a at h, etc. And this is g of order n actually. Okay, so by the induction assumption, the difference between f prime and this polynomial is a small o of norm of h to the power n. Okay, so this means that given epsilon positive, we can find a positive number delta such that the norm of phi prime of h, and this is, by the way, the operator norm here from E to F, is less than epsilon times the norm of h to the power n for h less than delta. And if now I pick h less than delta and I apply the mean value theorem to the ball, the convex ball, center 0 and reduced delta, I get phi of h minus phi of 0 norm is less than the maximum, which is epsilon hn, times the distance between h and 0. But what is phi of 0 if you go back? Phi of 0 is actually just 0, because it's f of a minus f of a, and all these terms are 0. So I get ultimately phi of h is less than epsilon times norm of h to the power n plus 1. And that's it. So this proves the theorem for n plus 1. Okay, so this is easy. Now, to prove the other versions of Taylor's formula, by the way, if you are tired, you can stop the video here and come back later. So, but I will not stop, I will continue, so I will cover all the sections. So, in order to prove the other versions of Taylor's formula, we need to establish two preliminary results. Okay. One is something that we didn't state explicitly, but this is something that you can deduce. When you have a function from an interval I of r into a normal space, then we can write the derivative. So if g is differentiable, we can write the derivative at some point t0. Then the derivative of g at t0 can be computed by the limit of Newton's ratio, actually. Know that if f equal r, but the same argument. So we can think of g prime of t0 as an element in f rather than a linear map from r to f, because a linear map from r to f can be identified with an element of f, as you know. Okay, so here we have the familiar definition or way of looking at derivatives. So derivatives here are elements in the target space, provided, of course, the source space is R. Okay, and as you know, we may use this convenient notation d over dt, which is mostly used by physicists, but it's very convenient actually. So this is just another notation for this. Okay, so let us formulate explicitly a form of the product rule. So once again, we have two maps. One, so both defined on some interval I of r. The first one takes values in R. The second one takes values in a normal space F. And suppose that are both differentiable at some point t0. Then their product is differentiable at t0. And the derivative of the product is the usual product rule. So f g prime plus f prime g. Okay. Now, there are at least two ways of proving this. We can prove this by invoking proposition 2.6, which gives the derivative of a bilinear map. Okay, so because fg is actually what? So here the bilinear map of f and g is just the product. Okay, so if you apply this with this chain rule, you will get exactly this. But there is another way. We can prove that directly. Just evaluate the difference between the value of fg at t0 plus h minus the value at t0, and we add and subtract. This is a typical trick. So we add and subtract the same number, which is f of t0 plus h times gt0. So we add and subtract it, and then we write the difference in this way. Okay, so and then we divide by t and or by h exactly. Sorry, because h is now a number. So we divide by h. We use this characteristic of derivatives, and you get precisely. So when we divide by h, this term goes to g prime at t0. This goes tends to f of t0 because f is continuous at t0, and this term stands to the derivative, and this is just constant. So this is the familiar product rule that you can use in this form. Okay, second result. If we have a function v from an open interval I of R into a norm space, which is n+1 times differentiable, Frechet differentiable, of course, then the derivative of this expression, v of t plus 1 minus t v prime of t, here of course we consider v prime as an element in f, plus 1 over 2 factorial 1 minus t squared v double prime, etc. The last term is 1 over n factorial 1 minus t to the n vn. If I differentiate this with respect to t, I get 1 over n factorial times 1 minus t to the n times the derivative of order n plus 1 of v. Okay, there are several ways to prove that, but in my opinion, the easiest one is just to reason by induction. If you take, for example, n equals 0, let us say, so all this cancel, so just get v prime, and here we get 1 minus t to the 0 is just 1, so we get just v prime. You can prove it for n equal 2, if you like. And now, in order to prove it by induction, you need to use the previous lemma. Okay, so if you suppose that this is true and you add a term, okay, so you have to differentiate the extra term. So you get here two terms, and you get here something of the form f prime g plus g prime f, and then okay. So it's very easy. In the book of Cartan, they give another proof, but I think this is simpler. So just write it. Okay. Corollary. If v is a continuous function from the closed interval 0, 1 into a norm space f, which is n plus 1 times differentiable on the open interval 0, 1, and whose n plus 1 derivative is bounded by some constant m, then v1 minus v0 minus v prime of 0 minus 1/2 v double prime minus etc. 1 over n factorial vn to the 0 is less than this constant m divided by n plus 1 factorial. Okay, this is just a consequence of the lemma and the mean value theorem, because we let u of t denote this expression, right? So if we put instead of t 1, then all these cancel, so just get u of 1 equal v of 1, and u of 0 is just v of 0 plus v prime of 0 plus etc. Okay. But now this lemma 4.4 tells me that can be written in the form u prime of t is equal to this guy. Okay, so when I take norms and I use the assumption that the norm of the n plus 1 derivative is less than m, I get this estimate. Now, of course, this is less than m over n factorial if t is between 0 and 1, so I can get rid, but I can use that, but I will use actually the stronger form of the mean value theorem by introducing this function g. Because if g is this minus m over n plus 1 factorial times 1 minus t to the power n plus 1, its derivative, just a function from r to r, or from 0, 1 to r, its derivative is just this. Okay, so the previous lemma, or this inequality, can be written as norm of u prime of t is less or equal than g prime of t. And if you apply the stronger version 3.4, I get the norm of u1 minus u0 is less or equal than g1 minus g0, and g0 is precisely minus m over n plus 1 factorial, and g of 1 is 0, so get exactly this. And this proves the result. Now, if we just took m over n factorial and evaluated or used version 3.3, then we would have get here m over n factorial. Okay, so this version of the mean value theorem gives a slightly better estimate. Okay, in practice it's not so important. We'll see why, but this is in principle a better estimate, slightly better. Okay, So this is one application of version 3.4. Okay, now we are ready to prove Taylor-Lagrange theorem. So under the same assumption, if the n+1 derivative is bound by constant m, on the segment joining a to a plus h, because we have to assume that the straight line segment joining a to a plus h is a nu in order for the theorem to make sense, because I need to evaluate f at a plus h and f at a plus th, where t is between 0 and 1. Now, if u is convex, it's enough to assume that a and a plus h are nu. Okay, or you may assume simply that h is small enough, which is the practical assumption that we will put in practice. Okay, so then the difference between f of a plus h and its nth order Taylor polynomial is estimated by this, and so for h small, the remainder is a small o of norm of h to the n. Okay, so now this is a consequence of the preliminary results. So we set v of t to be f evaluated at a plus th, t between 0 and 1. Okay, so our assumption that the straight line segment joining a to a plus h is a nu means that v is well defined. It's continuous on 0, 1 and differentiable on an interval bigger than 0, 1, but in particular it's differentiable on the open interval 0, 1. And now if I use the chain rule, I differentiate with respect to t. The chain rule gives me f prime, so the derivative of v at t is f prime of a plus th evaluated at h. You can use the chain rule, or you can go back to the definition if you like. If we differentiate another time with respect to t and use the chain rule again, you get that v double prime is f double prime a plus th evaluated at hh, okay, or h squared. So you can use this. So all the rules of differentiation are the same that you learn at school, but here instead of numbers we have linear and multilinear maps. Okay, but formally it's the same. Okay, and the n+1 derivative is f of order n+1 at a plus th evaluated at the vector h and times n+1 times. And now our assumption that the nth order derivative in the straight line segment, actually you usually assume that fn+1 is bounded on u, but we don't need that full assumption. Just need to know that the n+1 order derivative of f is bounded on the straight line segment joining a to a plus h. So when I take norms here, the norm of vn+1 is just take the norm here. I get and use the fundamental inequality linking multilinear maps with. So the norm of this is the norm of this, which is less than the norm of the multilinear map, which is less than m, times the norm of the vector h and times, which is norm of h to the power n+1. Or actually you have to, it's not the norm of the vector h, is the norm of the first component times the norm of the second component times the norm of the third component, and so on. Okay, this is the fundamental inequality linking the norm of a multilinear bounded map, okay, that we discussed in chapter 1. Okay, so if you apply the previous corollary, but instead of m we put m norm of h to the power n+1, we get this inequality. And now if I replace, so v of 1 is just f of a plus h, v of 0 is f of a, v prime of 0 is just f prime of ah, v double prime of 0 is f double prime at ah squared, and so on. So I get exactly the difference between f and its nth order Taylor polynomial, and that's it. So this is very easy. Okay. Last form, Taylor-Cauchy or Taylor of the integral remainder can be easily proved by using lemma 4.4, but the problem is to define what do we mean by the Riemann integral of a map taking values in a Banach space. Okay, the Riemann theory that you studied in second year can be extended, actually, this more general context, but if you look closely, you will see that we need the assumption of completeness of the target space. Okay, so we can give a meaning to the notion of the integral from A to B of some function, but we have to put assumptions on the function. If it's continuous, it's fine. Okay, but we can define integrals to what we call Riemann integrable functions. Okay, they include in particular continuous functions. They include functions which are piecewise continuous, and so on. Okay, so here everything is continuous. So having defined the Riemann integral of a Riemann integrable function from compact interval AB into a Banach space F, we can prove the fundamental theorem of calculus that you know from school, which states that if G is of class C1, then the integral of the derivative is just the difference. This is the familiar rule that you know, the difference between the antiderivatives, okay, or just G of X or T between A and B, okay. But this is not something trivial actually to prove, okay. Now, what do I mean by C1 if you are picky? Because you know what is C1 on an open set, but what do we mean by C1 on a closed set? C1 on a closed set means that three things. G is continuous first on the closed interval AB. It's C1 on the interior, and its derivative has a left limit at B and the right limit at A. Now, you can prove that if this is true, then we can extend G to a C1 function from R to F, if you like. This is very easy. It's a good exercise. So here, G is C1 means that it's C1 on an open set containing AB. Okay, when the domain is an interval of R, it's the two definition coincides. Okay, so having done all this, I didn't do that, but you can look at the book of Azé, where this is done, and you will see where the assumption of completeness is used. So having done this, then it's very easy to prove Taylor's formula of the integral remainder. Okay, so this is the form. So Taylor polynomial, and the remainder is given in an integral as an integral. And this is very easy. Just integrate the identity in lemma 4.4 from 0 to 1. Okay, and apply it to V, which is f of A plus th. Okay, so this is very easy. But we shall not use in this course this formula. So this concludes section 4.2. Thank you for your attention and see you next time.